All right, let's kick it off. Hi, everyone. Thanks for taking the time to join us today. The main focus of our talk is going to be about how integrating AI into long-term scenario analyses can deliver more accurate outcomes, even as the climate and weather patterns continue to shift. So we're going to take 30 minutes to really dive into it, and we'll save some time at the end for Q&A. So please feel free to use the Q&A box throughout the presentation. We'll take note of all questions and we'll go through them at the end of the talk. And as a reminder, we are recording this presentation and the recording will be available after today's session. So let's get into it. As mentioned, our focus today is long-term water forecasting. Our main presenter is Laura Reed, who has 10 years of experience in conducting hydrology-related scientific research, focused on water management, climate change analysis, and water resource systems modeling. Laura is our head of product strategy for HydroForecast, which is one of our 2 products here at Upstream Tech. So I'll give just a little bit of an overview about us and why we're speaking on this subject today. HydroForecast is a theory-guided machine learning model. Our team is made up of software engineers, machine learning specialists, and hydrology experts. And it's our mission to make weather and water data actionable by delivering hydrologic modeling that is accurate, agile, and decision-oriented. So HydroForecast lives at the intersection of hydrology and data science. And today we're going to get into how the model is uniquely positioned to answer questions on how flows might change in a basin over the coming decades. So on that note, I'm going to pass it over to Laura to start the discussion on long-term modeling.
Great, thanks Alexis, and thanks everyone for joining. I'm going to hop right in and just define long-term for this conversation and do that by looking at a plot here from the Climate Action Tracker, which essentially is showing out between now and 2100 some different pathways that our emissions may take. And so these bands and lines are showing that depending on our policies and how we make decisions as a society, our emissions could end up in very different places. And that leads to differences in how our climate will respond to those. So maybe the first thing to note here is that the uncertainty in all of this starts with humans, which is always very difficult and makes the problem maybe even more challenging. But we're really excited to be in this space and to bring our expertise and what we're doing at Upstream Tech to answer some of the questions and big challenges associated with making decisions for this cycle. So what are those decisions? What types of decisions have we heard that folks are making? I'll give a sort of sample here of folks that we've talked to and work with, and I'm sure there are more, so excited to hear from others. But things like investments, so new investments in, let's say you're thinking about building a forest, or you're maybe gonna look at new sites for hydropower that depend on a certain amount of flow. Maybe the forest, the species that you're thinking about could not survive above a certain temperature threshold. So looking at new investments and trying to make decisions now for these really, really far out times. Then we have existing infrastructure. So will your current systems that you have hold up? Will they produce the same, less, more during a shifting climate? We also have folks that are planning for water supply. So providing our cities, our industries, agriculture with water, not only total magnitude, but at certain times of the year when we need that water. Folks are making decisions now. Should they be investing in more storage? What's the outlook? And then finally, on the environment. So we've got groups that are looking to protect the environment, certain habitat and species that may not survive if temperatures of water or riparian areas increase or flows decrease. And so they're making decisions about adaptation now, so before it's too late for certain types of species. So this is just a sample. And I want to start by just talking about current approaches, like what's out there to make these types of decisions and understand the risks, and then use that as a way to go into how AI can help with these types of decisions, and then bring us into the picture and what we're up to at Upstream Tech. So starting off with kind of a range of current approaches that are out there. The first one is, all right, I need to make my decision. Am I going to invest? Am I going to build? Am I going to how can I best plan for this long-term future? Maybe you have no data. Maybe you don't have anything from the past in this region that can help you understand the future. And so you're basing that decision on qualitative research, things from the internet, IPCC, which will put out, like, for this region, temperatures could go up 3 degrees. And so that's something that we can all do from the science that's out there. Maybe a step up from that default option, is you do have some information about the past. And so you can make this assumption that the past is a predictor of the future. That has been something that has been a good idea in the past. I don't think I need to maybe spend too much time on why that is breaking down, and especially in certain regions and environments where we can see that more extreme behavior is happening, and taking the past rainfall or stream flow as something that would be a good baseline for the future would be difficult. And maybe one layer beneath that, not only are we looking at changes in how stream flow in the past is not particularly indicative of stream flow in the future, but breaking that down into the components, the variables or the inputs. An example here is, okay, let's say the average rainfall of the last 20 years was 14 inches. And from that 14 inches, you usually get about 2 inches of runoff. What we're seeing is actually those relationships are breaking down. And what that means is that essentially those models that were built on these relationships are potentially no longer able to predict into the future those internal kind of input relationships. And then we'll talk about what that means and how AI can play a role in that next. So then other options besides sort of baseline and default options of no data or using past data would be to conduct kind of a custom or tailored analysis. And so folks, either consultants externally or internal in-house capabilities, you can essentially go get all the data, process it, gather it, and build a hydrologic model, calibrate it, and actually get probably the data you need to make that decision today really well. And so the question there is that sustainable? It takes a lot of time, a lot of resources, a lot of compute to do so, but it's going to help you answer that decision today. Another thing out there are public products. So NOAA and the Department of Energy in the United States have put out some guidance on climate. They've put out gridded stream flow across the US. And so that's really useful if you're in the US. I think the questions there are, you do have to do some post-processing. So you've still got to process the data, pull it in, bring it to your system and basin to get the data out of it, or to also get insights out of that data. And also, you have the risk of, will that data be updated? What's the hydrologic model underlying all of that? So the question is kind of, what else is out there? What else can we do? And I want to frame that in the sense of how AI can be used to kind of approach this. And to do so, I'll start with some big challenges, especially that hit on this long-term scale. So without going too far into the philosophical thoughts here, I want to just start with memories. Talked about this on the last slide a little bit, but our models are forming memories. They're forming knowledge about systems. And those memories can be great because they can help the model go into the future and predict. If they're too rigid or they're too structured and they're holding patterns that are breaking down, then they may not be great for looking at this time scale and being able to adapt. We're already seeing how in the Western United States, a typical snowpack to runoff relationship is changing. And there's still a lot of questions out there in the science of why that's happening, sublimation, things like that. But the question is, how can our models, and can our models pick up on those changes and things that we haven't even seen yet happen in the future? Okay, the second one is the data chase. So it's intensive to not only go get all of the different sort of climate scenarios, which they now call shared socioeconomic pathways, or SSPs, but for each of those SSPs or emission scenarios, there's different climate modeling groups that are producing projections. And so you end up with a lot of different ranges and time series of precip and temp, which is great because you can build a whole distribution, but you've got to get all that data. And then once you run it through your model, how do you pick out the signal from the noise? How do you make that data actionable? It's a lot of work. The third challenge is CMIP. So it's great. Science is advancing. They're putting out new data sets. But the sort of second clause of that sentence is, oh, do I have to start over? How do we actually build a system that means when data and new model updates and new advancements in science is released, that we can most seamlessly incorporate that into our process and not have to begin again with recalibration and reprocessing of the data. So these are some big challenges, and AI is actually pretty well suited to help with them. So I want to talk about that next. Starting with the memories. So models making memories. The question is, can the memories that that type of model is making evolve? And the thing about AI and machine learning models, I'll sort of preface this by saying AI is a spectrum. You can have a really great AI model. You can also have a poor performing one or inefficient one, and I'll talk about that on the next slide. But the slice that I'm talking about is the type of model that we're trying to build, the type of service at Upstream Tech. And so for a model to be able to evolve, it has to learn in a way that doesn't mean that the parameters are specified to the relationship not changing. So here I'm showing an example of vegetation and snowpack. Our model is actually learning to observe. These models observe different data inputs and how those relationships exist. And if you train and build it correctly, it can see that in many, many different types of situations and actually learn how to predict outside of what's happening in its really small specific basin. So building a model that can adapt as patterns change and as relationships change is really important for being able to predict into the far future. Okay, number 2, go with me here. Data woes become data woes. This is my corny saying for basically, if we know anything about machine learning and AI, it's that it's really efficient for processing lots of different types of data. You can structure pipelines to pull it in very well. And what that unlocks is essentially the ability to do rapid speed improvements. So that I was listening to a talk recently that talked about essentially the time scale of advancing these types of models is just so much shorter than what we're used to because of how fast it can process data and then how fast you can experiment with it. And that kind of leads into number 3, which is talking about model updates. So what happens when CMIP 7, 8 come out? What happens when our models advance? Combining these machine learning type models with efficient data pipelines can just really speed up that research to operations cycle, making it seamlessly updating. In the sense that if you have a new data stream that you bring in, it's not going to require a whole bunch of work to go back, train a new model, validate that model, and make predictions. Okay, so I alluded to this on the previous slide, but not all AI is created equal. There are ways that you can actually make an AI model less efficient and even poorly constrained in the sense of getting worse predictions than a typical model would, a typical traditional model. And I want to just highlight an experience that we had with this, which was from a 1-year competition of streamflow across 19 sites in North America. The regions are on that bottom plot there. And essentially, you want your model's bar to be closest to 1, so the highest bar. You don't want it to be at 0. You don't want it to be negative. And so our model here was that blue one, that theory-guided statistical model. And the highlight I want to show here is that the beige model, the statistical model, the purely AI model, was actually the worst performing. And essentially what that means is that you can train a model on data, not constrain it, and not sort of involve the theory or incorporate that into the core of the model, and it will not make a good prediction. And so we need to combine the science with the AI technology and benefits in order to get something that holds up and can make reasonable predictions. And that's essentially what we're trying to build here with HydroForecast. And Alexis already introduced essentially how we're thinking about this and the type of model that we have. But just for briefly, HydroForecast is an operational modeling platform. It's unique. We have peer-reviewed publications on the type of neural network that is underlying it, and why some of the reasons that our model performs really well are kind of embedded in the discussion we just had, and also in the types of data and how we're processing that data and how we're training our model. And so today we're talking about our long-term product. We have other product horizons in which we're making forecasts. So short-term, looking at 10 days, that's for like floods and operational decisions. Seasonally, we're looking at water supply. We can look back into the past, and we actually have to do that in order to validate this climate long-term model. And then another product called our virtual gauges, which I'll probably give another webinar on, is essentially drop a point anywhere and get the best guess of what stream flow is, weather, anywhere in the world at ungauged locations. So I want to kind of focus the rest of the presentation on our long-term. How does it work? What does it unlock? What are the types of decisions and questions we're asking the model and folks are asking for this data? And then end with an example. So walking through the workflow, what is the long-term model? How does it work? Essentially, we start by teaching a core model, hydrology. So we open up a classroom, metaphorical classroom, and we invite 500 basins in from across the US. And so we have information about some of the inputs are basin characteristics. We have minimum and maximum daily temperature, and we have daily precipitation. And for our long-term model, we're looking in the past, we're training that model 25 years of data from 1980 to 2015. And we're asking the model, okay, go learn hydrology, check out how temperature interacts with this elevation, interacts with this precipitation, and really learn the principles and theory behind hydrology. And then output stream flow and also snow. So I want you to learn hydrology in a way that allows you to give me an output of daily stream flow and also snow extent. So then we test the model. We give it a big exam and say, all right, how well did you learn hydrology? And we do that by using USGS gauges for stream flow. And for snow cover, we're using a snow index, and that's from a satellite from MODIS, which is now VIIRS. And so I'll just stop right here and say this is the only neural network or even hydrology model that I know of that can actually output both snow and stream flow in the same model. And I'll talk about why snow is so important in a minute. So, okay, let's say the model passed the test. It needs a really high score to pass our test. It's ready to go out into the future, out into the world, and project out to 2100. So from there, we go and grab CMIP6 downscaled projections. We're using a source called Carbon Plan right now. I encourage everyone to check it out. It's really an easy way to pull time series of these climate projections of precipitation and temperature from different emission scenarios or SSPs. Different downscaling methods are available. And so you can really get a range of traces there from these groups. And then we run those through our HydroForecast model, and we get a time series out to 2100. Big picture, what do you get out of this model? What are the outputs? I have some listed here on the left, but essentially we can interrogate not only the outputs of the model, the stream flow and the snow, to get insights about trends and thresholds, but we can also access the precipitation and temperature because some of those changes and trends are just as important. This model is global, so this will work anywhere. Because we've trained a core model using real data, we can do this in ungauged places, and I'll show an example of that in a minute. We're also building tools on how to interact with this data and engage with it in a way that brings out that actionable science and actionable decision making. And this model updates so that process of kind of bringing up the new science and latest data service is seamless. I want to show an example here on the right of a customer where we did this and sort of what their decision was. So they're looking to invest in a lake or some infrastructure on a lake. And they're not going to invest if the flows are too high. They're not going to invest if the flows are too low. They're in the sweet spot between those dashed lines there. And so when we run all these different climate scenarios, SSPs, from different modeling groups, we get a range of outcomes that are possible. And some of those outcomes in the extreme sense could be above the threshold. We didn't find any that were below. And so with this type of information, that customer can say, okay, I am willing to take this risk, or I'm not willing to take this risk. I want to talk a minute about snow and why we explicitly include this as an output. For folks that have snow in their regions, it really drives the overall availability of water, especially from a water supply perspective. And it actually also leads to lots of other compound hazards that can occur when changes in snow are observed. And so I have that listed there on the right, where if you have an earlier snow melt season, which is happening, and you have less snow overall, that's essentially going to expose the soil to a longer period of dry. And with that, you have higher wildfire risks. Your crop can need more water, that crop coefficient's changing, and lots of other things that can occur from changes in snowmelt cycling. And that's one of the big drivers of why folks are really looking at this, especially if you are not only a snowy basin, but in a glacier basin. And so our model explicitly is predicting snow cover and stream flow to understand these changes and shifts and patterns. And I'll just show an example here from the bottom. So this is from a site in our core model, one of those 500 basins, and it's during the validation period. So this is during the big test. Can the model reproduce snow cover and stream flow? And so the red line there is our predicted snow cover over the validation period. So it's from 2015 to 2020. And then the gray line. So we want that red line to meet that gray line. And it's pretty good. We can always look for improvements. Then on the stream flow side, we want our model's blue predicted flow to overlap the black line. That's the observed flow. Pretty good. So again, we're always improving on this model, but we're seeing a lot of indication across all these basins that our model can predict not only stream flow, but also snow. Taking an example in the Pacific Northwest to kind of walk through just an application of this. So here on the right, we've got a basin. One of the upper catchments, subcatchments that isn't specified here has a glacier in it. For certain organizations that have a glacier, that glacial base flow in the summer is basically a large contribution of the overall flow, and it's critical. And so a lot of folks that have glaciers in their basin are wondering, when will that glacial flow go to zero? When will it reach a critically low level in which I can no longer rely on that dry season flow? So to answer that question, we actually are looking in this plot at September. September is in this part of the country a time when the snow has melted from the spring and it hasn't started snowing yet, usually. So any snow cover is actually glacier cover. And the discharge is usually very, very low during this time. So what we did was we took all these different SSP scenarios and ran them through our model. And so each of these different lines is a trace output from our model. The top one is stream flow, the bottom one is snow cover. The red lines are from SSPs that had warmer temperatures. The blue lines are from colder temperatures, and the gray are no change. I'm not showing here precipitation, but it essentially had no trend in it. So a lot of this change is driven by temperature. And you can kind of see over there on the right in that spatial plot how the temperature is changing throughout the basin. So that's something else that we can do, is look at this in a sub-basin sense and understand where those changes in which parts of the river and basin are occurring. But essentially what you see here is starting at about 2070, that snow coverage or that glacial coverage really drops off. I mean, there's a decreasing trend the whole way, but we can sort of answer their main question of when will this spatial flow reach a critically low or zero level? And according to these warmer temperature scenarios, that could be around 2070. And we see that response also occurring in the stream flow. So putting these two things together can really help explain what the model is seeing and why it's making the prediction that it is. So that's just one question that this data can unlock. But beyond that, I have a few other ones listed out there that we've heard from folks and are working with folks to help answer. And I think ultimately, we're really interested in interrogating the data so that it can help answer a decision. and even start to get at some of those compound hazards. So, okay, we see changes in the snow. What does that mean for wildfires? What does that mean for crop yield and agricultural needs? I'm showing an example here from just how seasonality could shift. So maybe you're used to most of your snow melt occurring in July. How could that change? How could the distribution of that change according to different SSPs? So those are just some examples. And we need more examples, so tell us so we can build those in. A minute here on upcoming R&D. So we're excited about what we've built already, but there's more we can do. We're hearing from folks of more needs that they have. So one of the things that we're experimenting with is how to include extremes. It's pretty well known that the typical global climate model isn't able to reproduce these really, really big extreme storms or extreme temperature shifts. So some things that we're working on are taking past events, which I would be contradicting myself if I said we took the past and used it as a future. So we take past events and we can develop a synthetic distribution around those and actually run that distribution through the model to understand how that past event and things it hasn't seen before could play out. There are some data sets associated with CMIP6 where extremes are preserved in the sense that they're taking the statistical downscaling and ensuring that you're not losing all of that variability. And so we've pulled that data in and we're starting to experiment with that. On the kind of tool side and data side, we're excited to basically start building something where this historical and future climate data could be available on the fly. So imagining a web interface that's associated with our dashboard where you could go in, delineate your area, give it a lat long or a region, and you could receive that historical precip and temp data and future data pretty quickly. Our hydrologic model runs actually in like 1 second. So it's gathering that data. It's pretty quick, processing that data, a couple hours right now, but we want to get that really fast so that we can serve a lot of different folks and make the data more accessible. Another kind of more technical, weedy one, but we're excited to work on because it can unlock a lot of risk-based decision making, is how we combine probability distributions. So our model is a neural network that produces the full range of probabilities, all the quantiles of flow. So that gives you a nice sense of uncertainty. But when you start stacking together all these different SSPs and climate groups, then you start to have all these overlapping distributions. And so the question is, how can we create aggregated distributions so that someone could say, okay, my 80th percentile flow actually means that I can understand how likely this is to happen. And it can sort of combine all of these different traces in a way that's useful. So those are some things that we're working on now and excited to work on. And maybe just, this is the final slide, just like a thank you for coming. We're excited to hear from you and your feedback. Some takeaways on how AI can be in this space and what we're excited to do with our product and service. And just, yeah, want to just open it up for questions and thank everyone again.
Thanks, Laura. This is great. So we do have the Q&A box at the bottom. So if you have any questions for us now, please feel free to drop those in. And if there aren't any current questions, Laura has included her email here on the screen. So please feel free to jot that down and we can answer any questions via email after the fact as well. In this recording, we'll be going out to everyone here, so you can refer back to it or pass it along to your team later. All right, Laura, we have one question that just came through. So to make sure that they understand, this approach uses CMIP, but skips the other models, the Canadian model, the US model, the university's model, etc. Is that correct?
Yeah, great question. So right now we've built this product and model so that it can be global, and the CMIP6 data is global. There are certainly some instances where we can look at incorporating some more regional projections, but we haven't done that yet.
Okay, I think that might be it for current questions. Like we said, please feel free to reach out to us if you think of anything later. We're happy to get in touch. Thank you all for taking the time to join us today. Have a good rest of your day.